This is part 2 of our 3-part series, where we make sense of the alphabet soup of acronyms for database consistency models. In this episode of Mobycast, we learn how the explosion of the internet created new challenges for strongly consistent systems, leading to the discovery of the CAP theorem. The CAP theorem reminds us that as systems scale, errors will become more likely, forcing us to choose our priorities. We also learn what Chris shares in common with Eric Brewer, the creator of the CAP theorem. It's a roller coaster ride that comes to a crashing halt. Welcome to Mobycast, a show about the techniques and technologies used by the best cloud-native software teams. Each week, your hosts John Christensen and Chris Hickman pick a software concept and dive deep to figure it out.
Welcome, Chris. It's another episode of Mobycast.
Hey, John. It's good to be back.
It is not just another episode of Mobycast. We are here at number 100. 100 times we've done this. What do you think, Chris?
We're a 3-figure podcast.
Yes, we are. And maybe, Roy, can we get a little bit of Auld Lang Syne with some cheering? Thank you. This is so fun.
Some audio confetti.
Yes, so good. So good. Everyone's celebrating with us in their cars on their way to work right now.
So I have to ask you, did you ever think we would get to 100? Like when we started, right? So we were there having lunch in Denver with Rich, and kind of like the genesis for the idea is like, yeah, let's do a podcast.
Yeah. You know, I guess I never thought about it. I never imagined what that would look like. But I guess I would say that if I had imagined us going to 100, I probably would have expected that we would have more than our 12 listeners that we have. I mean, 12 good folks. I really like all of you.
Right? You think you know, analytics are pretty difficult here in the podcasting space. They leave much to be desired. So, you know, pick a number. You can pick 12. I'll pick 12,000.
Right. No, it's definitely more than 12. I at least met, I think, a 13th person at one point. All right. So enough self-deprecation and celebration of our episode number 100. We're still talking about databases. We're doing this sort of database soup little mini series. And the soup last week, I felt like the soup was a little bit acidic. So maybe we can kind of even that out with some CAP theorem and base today. What do you say, Chris?
Sure, absolutely. So we were down the low digits on the pH scale, and we're moving our way up. So I think 7's neutral, and so we'll call that CAP. And then after that, we can move into base and get above that. Flexing
your high school, that is just a great flex right there. Your high school chemistry memory.
It's all about the base. Yeah. We could go on and on, folks, but we won't. Yeah. So
this is. Let me just kind of frame this. You know, why is it important? Why? So what? Right? Like, who cares? Just give me the API. Let me put my data in there and move on. I think why this is interesting is for one, Chris and I are old and we lived through this stuff. Like, this is really interesting for me because, honestly, I kind of stopped paying attention to the more academic type stuff after I got into my professional career. So I didn't really know until more recently what the CAP theorem, and I hadn't really heard of this base thing before. I definitely heard of acid because that came out of my way long ago cabin in the woods education that I got. So this is interesting for me, like having lived through this and seen the changes and touched the stuff. And I think it's interesting just to also like you, Chris, stayed close to this and you actually were involved in this in your real life, like in company that you founded and then in just thinking about it ever since that company, because that company, I think, has sort of shaped who you've become as a developer. So it's kind of interesting to see, to listen to it from your perspective and to have you be the character in this story of databases changing and what we do about it and how we learn about them and think about them.
Yeah. And a few months back, I kind of threw together some notes, kind of saying like at some point, definitely should talk about like acid and base and CAP. It's pretty fundamental to just talking about databases and distributed systems. So we should talk about that in a future episode of Mobycast. And been wanting to put together a series on databases and how they've kind of really branched out. It used to be we just had relational databases, and now we just have a whole suite of different type of databases that are purpose built. And it's really been driven by the use cases that we're seeing now. And that's been driven by large scale systems, the internet, the web, cloud computing and whatnot. So I figured let's talk about acid, cap, and base before that, right, to lay some context. And honestly, I was kind of thinking like, oh man, this is going to be kind of boring talking about acid, cap, base, and like consistency models. And it's like, well, let's just get through it. We'll do one episode of maybe, it's not going to be too terribly interesting, but it's important.
Right.
So we'll
Huge
talk about
horse pill
it.
vitamin episode. Yeah.
Yeah. I mean, it's even worse than security broccoli, right?
Right.
But as I kind of went through this and was preparing for it, I was just kind of blown away. It's like, this is actually, it is kind of interesting. And maybe it's, more for me just because this is just, it is really like a history lesson. And we went through this. Like we went through these, like we're talking about like discussing this in a series of 3 acts, a 3-act play of consistency models. And act 1 being the acid era. And that served us very well until the internet came along, and in particular the web, and things just started getting much more complicated. And then that kind of led people to this discovery of this cap theorem, which we'll talk about. And again, I was right in the thick of that, like running into the exact same issues and problems. And then following with that, then we're like, okay, we have to make some accommodations here for this. So we're going to have a different type of consistency model for certain types of use cases. And that's where base came about. And all this is kind of interwoven with just personal experiences and what was going on at the time. But it ends up being like talking about acid, cap, and base. It truly is like it's a history lesson, and there's reasons why this stuff happened. And so kind of picking that apart, I think, gives a lot more color to it and turns something that could be really boring into something hopefully that people find really engaging and entertaining as well.
Mm-hmm. So are we going to jump right into the cap theorem, or just that, talk about what we're going to talk about today specifically? Yeah,
I mean, just real quick, just remind folks, last week we talked about acid. So that was act 1. So we learned about like transaction processing and the acid properties of transactions, which that's that 4-letter, acid is the 4-letter acronym. And so the properties are atomicity, consistency, isolation, and durability. So those are the 4 properties that go into defining a transaction. Like this is what a transaction needs to have, right? So we talked about that, and now we're going to get into Act 2. So the arrival of the internet, and in particular the web, creates new challenges for this, and that the problem of building large scale out systems really kind of leads to this discovery, if you will, of the cap theorem. So that's what we're going to start with today.
Right on.
So let's dive right into that. So the cap theorem, it was proposed by a computer scientist named Eric Brewer. Eric was in the academic world working, I think, at UC Berkeley, and kind of formulating some of these ideas around it. He was also, he was building systems as well. In particular, he was building a search engine, I think, in this time. Ended up spinning that out of UC Berkeley, and it became a company called Inktomy. And while there, again, this is like in 96, I think, is when he started Inktomy, and they're building software for the web. The web is now really kind of taking off. This is the time where, Netscape and Microsoft are duking it out, and the web is kind of exploding. We're starting to see scale that we've never seen before. And so he's running into Inktomy is running into issues, right? Like how do they scale out and accommodate all these users on their infrastructure software? And so basically he kind of notices that there's a kind of like a fundamental law going on here, if you will. And he calls it the cap theory or cap theorem. And so cap is another acronym. And so it stands for, there's 3 properties. So we have consistency, availability, and something called partition tolerance. So C, A, and P. And the CAP theorem basically states, look, in a particular system, you cannot guarantee more than two of those properties at the same time. So you can have consistency or availability, but not both if you also have problems with your network. And so partition tolerance too is a little bit...
Yeah, we need to get into what that means.
Sure.
What is that partition tolerance?
Yeah, so this is not like partitioning data or kind of things like that, right? This is actually about network partitions and really partition meaning a break. So one part of the network can't reach another part of the network. So we should just think of this as network failures.
Yeah, and you and I talked about this a little bit yesterday, Chris. And before we get into the example that we discussed, I just wanted to say that, so this CAP theorem, it uses mathy words, and it's like a theorem, and it's proven with math, and it's like, wow, it must be really complicated. And I think the truth is, like, after you get your, if you don't already know it, after you hear us explain it, you'll be like, oh, that's really intuitive. And probably, my guess is that Eric was kind of like, there's this intuitive thing that I keep running up against. I wonder if it's like a fundamental law of the universe. And then, let's try to prove it. Turns out it is. Like that sort of like intuitive feeling that if you have different computers that have information in them and you break the connection between those computers, that you have to make some decisions. You have to make some trade-off decisions. Like you can't have a network breakage between two computers and not end up making trade-off decisions with your product. And I guess I say that this is intuitive because I've been helping people make those trade-off decisions as we build software for like the last 20 years without knowing that the CAP theorem, without understanding and knowing the CAP theorem formally. And once I understood it, I was like, oh, I totally knew about that, right? Like totally have been making those trade-offs, helping people make those trade-off decisions. So do you want to give like the little example that we came up with yesterday, Chris? Yeah,
well, let me just kind of add to what you're saying there on how this is kind of intuitive. I absolutely, agree with that. It's obviously nice that we have this kind of like we have an acronym for it. It's been well defined and there has been the math behind it to prove it, to actually make it a theorem. But it really boils down to, so you have this distributed system with a series of nodes that all need to store state, right? And they need to be, you're trying to keep all of them have the same state. And so they're connected via a network. If things are going along fine, right, there's just no issues, right? It's just the system's working normally. But we know that like this is not how things work in the real world. Like things break, edge cases happen, and failures happen. It just happens, right? So if they are in the breaks, let's just for the purpose of this, we're just saying that the breaks are actually in the network itself. So when two machines are trying to talk to each other to maintain their state and the network fails, you have two choices. So if you update your first, if the initial system updates itself and then tries to go in and say, okay, now I'm going to tell this other system to update itself to keep it consistent with me. If it can't talk to that via the network, it has two choices. It can either say, all right, I'm going to fail this. I'm going to roll back. I'm not going to commit this to my database, to my state, so that the system remains consistent, right? So I'm valuing consistency in that particular case. So that's the one decision I could make. The other decision would be like, well, I'm going to allow this to proceed because I don't want this to fail. I want it to be successful. I want the system to be available. But now I realize that I'm in an inconsistent state, and I'm going to have to do something about that later. And so that's really kind of fundamentally what the CAP theorem is saying, is like when you have these network problems and you can't communicate to all nodes in a network, you just have two choices. You can either fail it and remain consistent, or you can let it succeed and now become inconsistent. So you're either going to say, I want to be available, or I want to be consistent. But when those network errors happen, you have to choose one or the other. And that's really what the CAP theorem says. And so that's right. Kind of, again, a little bit maybe theoretical. So why don't you go ahead and talk about...
Cool. I'm so excited. I've been saving this one up. All right. So in this little example, our nodes in the network are children. So I only have two and Chris only has two, but imagine I had many. Let's say I had 3 kids. And so those are my nodes in the network. And for the first example, I want to create a new state in the nodes of the network. So I want them to have like a memory of a wonderful birthday party. And I want them to store that memory. If 2 of my kids are at home and one of them is away, maybe staying over at a friend's house, then I may decide, actually, we need to hold off on this happy birthday singing song because, I wouldn't be creating a consistent memory. The network is broken. Like the kids are not all together, sharing the experience together, like able to keep their state together. One of them is away. One of them is partitioned off. So we just say, we're going to block it. We're going to keep things consistent, wait till the one gets back from the overnight, and then we'll do the happy birthday stuff so that everybody can have a consistent memory of being sung happy birthday to. And then in a different type of situation, I may be like, one of them is away, and I need the state that I care about is like just getting food into the kid's stomach. Like they just need to eat, and they need to go from empty to full, pretty much usually 3 times a day or more, 4 or 5 times a day. If one of them is away and off at the sleepover, I might be like, what's important to me is that I can do this function. I can do the feed function, and that it's available even if the network is partitioned. So I'm going to go ahead and feed the 2 that are here, and we'll worry about getting that other one fed if they're underfed on their sleepover when they get back. So in one situation, consistency was important to me, and in the other situation, availability was important to me. Just getting them fed. It didn't matter that the other one was partitioned off. So does that feel intuitive, Chris? Is that kind of like and then we can give other examples like your bank account balance. Like you probably care that that's pretty consistent, that you don't go to one location and get one answer and then another location get another answer. Like you really care that that's pretty much always up to date and right. And if that,
unless
for
the
some
error
reason,
is in your favor, right?
yeah. And if for some reason the like computer that you're working with is cut off from the network, or the network is like not all together, there's a partition in it, you may want your bank to just be like, hey, no, nothing's happening here until we're all together again. Yeah.
Yeah. I mean, we see this in just all the time, right? In everyday life. So it's not just computer systems. We're always making these trade-offs, right? Is this when something happens, does all of it have to happen, or can I handle just partial, right? And that's really what this is about, right? So again, the really kind of strong takeaway here that the cap theorem is just like when you have those breakdowns in communication between nodes, which will happen in a large system, you have to choose, do you want to value either consistency or availability? You have to pick one of those because you can't have both. Right.
One last example that I like is just like code management. So way back, we used to lock files and work on them. And nowadays we work on them separately and deal with merge conflicts. So way back in the day, we were wanting consistency over availability. And now we're like, come on, availability is what's really important. Let the team work.
Yep, absolutely. So when you value the availability over consistency, then, at some point later down the line, you have to figure out a way to resolve, right? And so like in the case of source control systems, we do merges. And so sometimes that goes really well, and sometimes it can be merge hell, but depends on
But the cap decision was made, right?
Yes.
The cap decision was made before that hell happened to you.
Yeah, absolutely.
Yeah.
So I mean, I think hopefully, we've explained cap theorem. It is pretty simple and pretty straightforward. And when you think about it, it's pretty intuitive, especially once you get past the terminology of partition tolerance, like what that means. And again, just think of communication breaks, like errors in the network.
Right. Yeah. And just because it's intuitive doesn't mean that it's not awesome that it can be proven. Just like 1 + 1 is 2 is intuitive, but the proof behind that is not so simple.
Right. Cool. And then maybe another thing I kind of just found interesting as kind of like a side point is that, when we were at reInvent this past year, the 2019 version, during Werner Vogel's keynote, he talked about like some of the problems that they had with EBS and they came up with a solution to make this that they were very proud of, right? To kind of reduce these error rates, right? To make it even more robust and more available. And so this thing they came up with, they called it Phasalia, and kind of going into the details. We don't want to go into the details. It's too complicated. But what was really kind of interesting that it was all based around like these failures that were happening with EBS that had to do with shared state among these nodes in the system. Just
quick interjection. EBS is elastic block storage. It's just sort of like network disks for EC2, Amazon's EC2 computers. Yeah.
Mm-hmm. Yep. So think of it as volumes that you can attach to virtual volumes that you can attach to your virtual machines. And so there's some shared state there for this. The EBS itself is a distributed system, right? It's not a physical device, one physical device. It's a bunch of physical devices that are all connected through software, right? Which is kind of mind blowing in and of itself. But anyhow, so they noticed that having issues with just this shared state, and they realized like, well, obviously the cap theorem applies here. And as they're looking at it, they're like, well, we have to be available and we have to be consistent, right? Think about it, like if you're reading and writing from like your virtual disk, like if you're getting different answers, right? Or if it's delayed, or one server's reading, some data that's different than another one, like that's not good. And then obviously if it's not available, if it's broken, that's not good as well. So they have to have both of those. So really that leaves like, okay, it's the partition tolerance thing that they have to really work on. And so they have to reduce those network issues. And so what they did with Phasalia is all about reducing the distance between those nodes that have to keep shared state. So you can kind of think of it as like if you had two machines that were trying to keep consistent and talk to each other that were located on different edges of the city, and they were going through multiple networks and different hops and different routers, like the odds of something failing along the way is pretty high. Versus if you had them together in the same room where it was just a single Cat5 cable connecting the two of them, then the kind of chances for network problems are going to be much less, right? So your network breaks, the rate of them is going to be much, much smaller. And that's what they've done basically with Phasalia. They've reduced the network between these things in order to provide a more robust design. So it's just really interesting where it's just an application of this, hey, the cap theorem is something that we have to obey. It's real. And how can we, by being aware of that, how can we design the system, right, to make it more robust?
Right. I like to think of that too as like, it's a reminder that the third leg of the table exists. Like you're not always just choosing between availability and consistency, that there may be things you can do to reduce that partition, reduce the partition likelihood. Mm-hmm. And so and I think it's really fun to think about the EBS problem as like, well, people are used to having a hard disk in a, tower PC they have sitting at their desk. And there's no issues with a partition happening on that, right? Like it's connected directly to your motherboard, and either the whole thing works or the whole thing doesn't, but it's always available and it's always consistent. So there's no problem. The P is gone out of the cap theorem. So you've got that, you've got A and C. So it's like what they kind of did was like when you were first saying it, I was kind of laughing because you were like EBS, it's not just one big disk. And I'm sort of like, wouldn't it be funny if it was like one disk the size of Houston? And that's sort of what they did. They're like, what can we do? Like to make this behave like one disk? Let's put everything really close together.
Yeah. I mean, it's still not one disk, big disk like Houston says, but it is like that ended up being core to the design is like, how can we, it really is kind of just interesting from the standpoint of like, what's the algorithm to kind of understand like what data is related that needs to be next to each other, right? Like what, so exactly it's the relationships between them. So that's where like a lot of this work comes into play is like, what is the algorithms for doing the optimal placement of data such that when they do have to talk to each other, like they're very close to each other. So now that I understand what the cap theorem is, and like Werner's talk like takes on a whole new life, and it's so interesting. And I know it's just Werner, since I know you're listening, it's like, know your audience. Like, yeah, it's a bunch of techies in there, but
honestly, that room's not full of people that are like, oh, well, it's a cap theorem. I mean, yeah, sure, there are some, but like not 80% of the people in that room were like, oh yeah, cap theorem. Definitely not 80%. So yeah, explain cap theorem if you're going to use it in a talk.
Request.
With examples,
PR.
right? Not just,
Is this your PR to Werner?
yeah, it is.
Yeah.
We cover a lot of information here on Mobycast, and if you've ever wanted to go back and remind yourself of something we talked about in a previous episode, it can be hard to search through our website and transcripts to find exactly what you're looking for. Well, now it's a lot easier. All you have to do is go to mobycast.fm/show-notes and sign up. We'll send you our weekly, super detailed outline that we use to actually record the show. A lot of times, this outline contains more information than we get to during our hour on the air. So sign up and get weekly Mobycast cheat sheets to all of our episodes delivered right to your inbox.
Yeah. And maybe just to kind of wrap up with CAP is like, the reason why we're talking about this as Act 2 is that it really comes into play with scaling, and in particular, the horizontal scale out, right? So we're going from, instead of like scaling up, which is what we did do before the internet really existed, right? Yeah, so we just got bigger computers, right? So if if you had doubled the load on your database server, right? You went and got a twice as powerful computer server, and now your database was on that, right? And so you just keep getting, but at some point you can't buy a bigger computer, and that's what we ran into when trying to scale to these internet usage cases. And so instead you go with the other philosophy, which is scale out, right? So you have a bunch of nodes, and you get into things like data partitioning and whatnot. But it becomes truly a distributed system with many different participants in it, and therefore you now have networking between them. With scale up, there's no networking, right? Because it's all on the one node. With scale out, you now have networking, and that's really what kind of drove the discovery, if you will, of CAP is it introduced the networking in between these nodes, and it became just a fundamental piece of the distributed system that we were building.
Right on.
So so we I think that's Act 2, talking about the CAP theorem. And before we go on to Act 3, thought it would be kind of interesting maybe to have a little bit of an intermission here and take a kind of a personal story detour.
I want to hear it. Let's hear it.
It's kind of interesting, right? Because we talked about Ink2Me. That was the company founded by Eric Brewer while he was at the UC Berkeley. This is in '96, and they were working on just the infrastructure for the internet. So they came out first with their search engine, and then after that came out with basically a caching platform. And that ended up becoming like the really, really important thing for them that really led to just this really fast, incredible growth, right? Because as the internet was scaling, things like CDNs, they didn't exist yet. And so things like Ink2Me, companies like Ink2Me were providing the software in order to enable those kinds of things. So, I had been working at Microsoft from 96 through 98. So about that time, that's when I was at Microsoft, and we were really working hard on how do we build our applications for the internet in the Microsoft network.
And whiffing at it too, by the way.
That's not my fault,
right?
Or even us. But the thing that we did have going for us, right, is that we had millions of subscribers on MSN, right? And so they had previously, MSN had been a dial-up service. Here comes the internet, and it's like, okay, the days of dial-up and these proprietary networks are gone. We really need to kind of rebuild this for the internet, right? And so that's kind of what I came on to do. And, very interesting, challenging problems. The thing that we had right out of the gate that really not many other companies had was the scale. We immediately had lots and lots of users because it's Microsoft and because MSN already existed, right? So
right, and it's like the desktop space, right? Oh, what's this icon? Click, click. And then next thing you know, you're in MSN.
Yep.
Yeah.
So while Eric is at Ink2Me, and they're working on this, scaling internet with caching and search engines. I'm at Microsoft. We're running into issues with like, how do we scale our data? Like it's really easy to scale the web apps, the front end web, and even application servers, but like the actual state, the data, like how do you scale that? Like there's not a good answer for it at all. So that was where we're spending most of our time. And so I left Microsoft at the end of '98 to go co-found a company that was in that space, right? Like how do we scale data? So we were trying to build basically an internet scale database that was backed under the covers by a relational database, but basically you can think of it as like a load balance, like being able to put a load balancer in front of a cluster of database servers.
Right. And definitely like for the deeper story on that, like listen to episodes 39 to 43, which we also mentioned last episode, but it's good stuff. Like Chris's storytelling, like one of the things that I remember, right, is that you quit your job at Microsoft and on your way home from your job, like the last day of your job, you just stopped by a VC company and picked up seed funding. So like before you even got home, you already had funding.
It wasn't that quick, but it was pretty quick.
Right. It was like during the time when literally probably VCs were standing out, like chasing around people that had Microsoft stickers on their windows. Like, are you going to quit Microsoft? Can we fund your new company?
Yes. It was, well, I mean, and so the thing, like, so interesting. I mean, it's like, this is the birth of the web, right?
Yeah.
Like,
and not to say that your idea, like that, I don't want to like discredit your idea at all. Like that there was money everywhere. Like you obviously were onto something. So,
right. Well, yeah. and I'm just pointing out too, it's like, there was money everywhere for a good reason. Like people realize this is a brand new thing that's going to completely change everything. And there's so much opportunity here, right? Like this is greenfield. This is a land grab.
And there's $4 trillion companies 20 years later,
Yeah, absolutely. So, and I thought so I was kind of looking, again, doing some of the fact checking and the research for this and looking at Ink2Me and Eric Brewer, and kind of saw a talk that he gave where he kind of went through a little bit of the timeline for Ink2Me. And I thought it was just super interesting because the timeline for Ink2Me really mimics the timeline for this company that co-founded this VC-funded company trying to build this internet scale database system. Like if you were to draw the graphs of these two companies and like their valuation, if you will, it's like, it'd be a really interesting graph because it would be it'd be almost like the exact same curve, just maybe Ink2Me's is a little bit more spread out. They had a little bit more on the edges, if you will. So like, just to give some examples. So I talked about like Ink2Me founded like in '96. They went public in June of '98. Like it's like seriously like two and a half years maybe. They go public. Less than 2 years later, in March of 2000, their stock peaks at $241 a share. Okay, that's $25 billion market cap.
Oh my goodness!
So, like, I mean, this is less than 4 years from creation. It's a $25 billion company, right?
It's just wild because I can't even like it. Kind of tickles a memory, like, oh, I think I remember a company called Ink2Me, but not really. I don't really remember it.
By the way, like a side note here, I was at this time, like it was fun. It was like, do you remember day trading? Like right? Yeah. So, I had my Schwab account and like I was just playing around. I remember buying like Ink2Me at $50 a share and like literally within 3 months it was like at $240. I actually, and it wasn't like a tremendous amount. I didn't have a tremendous number of shares, right? But it was enough to put in my backyard pergola. so my backyard, the hard landscaping in the backyard was paid for by Ink2Me stock. So I
thank you, Eric.
Yeah. So the stock peaks in March 2000, and then, fast forward 2 years, the dot-com bubble has burst, and the company's being restructured. like it's now down at like, it's like $1.53 a share or something like that, right? This is 2 years later. And then in March of '03, Yahoo acquires Inktomi for $241 million.
Nice.
That is 100x difference between their peak.
Oh, brutal.
Like just 3 years prior.
And Yahoo sitting around going, we just got a deal. Like, imagine our future. It's going to be so, right.
Yeah. I know. Yeah. I know. I don't know if you remember, Jerry Yang turned down the $40 billion acquisition offer from Microsoft.
Oh, yeah.
Right. And then we all know that, Yahoo was a $300 million fire sale a few years back to
exactly.
AOL or whatnot. Right. So, kind of crazy. So that was their timeline. Just kind of for reference, like with Viathan, which was the VC funded company that I was doing at the time for building this internet scale database system. So we were founded in February of 1999, and we did our seed round and raised $700,000. And then 6-7 months later in September, we did our Series A, raised another $6.5 million. And then in September 2000, which is about 6 months after Inktomi hit their stock peak, that's when we did our Series B and raised another $17 million. So at that point, we had raised $24 million in VC. I forget what our valuation was, right? But
that's what I wanted to know. That was my next question. So what were you worth? Like what percent of the company was that 17 million?
So I don't know exactly what the valuation was at that time. What I will tell you is that typically each round was somewhere around 25 to 30% selling off, right? So you can, like, if I actually had a few minutes and a calculator, we could probably figure out like pretty close what the valuation was.
Around 80 million-ish, probably, I'm guessing.
Something like that. Something like that, right? Then about 6 months after that is when we got now it's like the dot-com bubble is starting to happen, right? It's starting to, the wheels of the bus are coming off, and we're now starting our slide back down, right? There's now definitely some stink, if you will. But we do get a letter of intent to be acquired by EMC for $45 million cash.
Yes.
So, okay, this is still good, right? It's not great, but this is really still good. So pretty excited. And then a couple months after that, like in June of '01, EMC retracts the LOI, the letter of intent, because they're like, look, sorry guys, we're not going to go through with this acquisition. It just came down from our CEO that we're not doing any more acquisitions for right now because we're going to have a quarterly loss, and we're also doing layoffs for like the first time in like 18 years or something like that. So we can't go acquire companies while we're firing a bunch, thousands of people. So sorry.
Bad optics on that one.
Yeah, deal is off. And so then basically that was kind of like the end of that. A few months later, Viathan was acquired / merged with another company that actually built personal backup software for the Mac. Which, think about, like, internet scale database, and it's like, okay, you're going to mix that with backup software for the Mac, and that's a whole nother story of why that happened and the meaning behind it, and I'm not going to get into it now. But so you can just see, like, so with Viathan, it's February of '99 through basically October of '01, right, is its curve. And that is it goes from very low up to a very sharp peak and then comes back down. And if you superimpose that on Inktomi's, it's like almost the same thing. And like, it's true with many, many, many other companies as well, because it really is like that .com bubble. What happened. So you saw like there's this tremendous opportunity. We knew the internet was going to change everything. Move fast, right? And really don't worry about business model and mechanics of it. And then, kind of pay for that exuberance pretty dearly. But boy, what a fun ride.
Yeah. And That's exactly what I was thinking. It sounds like a roller coaster, and all the way to the end part where you like come into the station at the end, it's like, and like everyone kind of like almost like throws forward and hits the bar as it like instantly stops, and all right, get off, everyone.
That's it. Yeah.
Next.
Yeah, it's like Ferris Bueller at the end of in the credits. Like, what are you still doing here? Go home.
Yeah.
It's done. Go home. Yeah.
So that was a fun intermission. Maybe we should have all of our entire podcast be intermissions like that. That was pretty cool.
Yeah, hopefully.
I guess we're supposed to learn something too.
We did. We ate our broccoli early on. We learned all about CAP, and we got to play a little bit as well and tell a story. So we'd definitely love to hear feedback from folks. Like, let us know. Do you like this kind of color commentary, or we just let us know how we can improve, what we can do better, the kind of content you want to hear.
Yeah, because we're going to turn a new leaf after episode 100 here, so all new personalities, everything. So Chris, we have another part of this 3-act play to talk about. Is that going to be the third episode of a series?
I think so. I think so. So we've covered the first 2 acts, right? So it was the period of transaction processing and ACID that was kind of up until the beginning of the internet explosion. That kind of led rise to this discovery, Act 2 of the CAP theorem, and that now that we have these big distributed systems with networking in between the nodes, like that's going to cause problems. So how do we deal with it? And then that gives rise to this third act, which is basically, given that we have the need to store state, but we have these systems that are very, very large and need to scale to just tremendous,
and are prone
volumes.
To partitions, prone to these network partitions.
Right. So how do we deal with that? And so that gives rise to a new model of consistency, which is eventually will be consistent, right? So to kind of take off those really rigid constraints of making sure that everything in the system is completely consistent, instead kind of looking at it and asking ourselves, do we really need that? Can we take advantage of some certain constraints or use cases here and really, not have to have those strict, rigid requirements? And what are some of the things that we can do there? And that really kind of saved us and allowed us to now scale to these massive size systems. And so this whole concept of eventual consistency, which also really closely correlated to that, is our third acronym, BASE, which stands for basically available, soft state, and eventual consistency. So I think maybe we could save that for the next show, and we can dive deep into just what does this mean, and how to use it.
Sounds good. I'll be breaking my word because I think last episode I said we'll get this done in 2. As is our wont here on Mobycast, we're going to add another and get it done in 3.
Absolutely. Cool. And I think there are some again some interesting stories here, and kind of color commentary as well with BASE. So I think it'll be fun.
Cool. Looking forward to it.
All
Thanks so much for this.
Yeah. Thanks, John.
Yeah. Talk to you next week.
Okay. Bye.
Bye.
Thanks for being aboard with us on this week's episode of Mobycast. Also, thanks to our producer, Roy England, and I'm our announcer, Stevie Rose. Come talk to us on mobycast.fm or on Reddit at r/Mobycast.